think it's going to start recording. There we go. Okay, so today we are doing the second lesson for Unit 9. So after this, there will actually be a test that opens up to you. The Unit 9 review is open and available for you. This was a very short unit, just mostly a review of things we've learned with a little extra algebra, just a little bit more. Yep, the test is actually very short since it was a short unit, short test. Okay, so the question is, when is the Unit 9 test due? Let's see. You'll see the Unit 9 test show up on your plan on Friday. Its end date is March 11th. Why don't we say, you want to have that done by the 4th, just so that way it's done. Okay. And the Unit 9 test is actually going to be in USA Test Prep. So it's going to be a little different. When you click on the Unit 9 test, you'll see directions show up for the Unit 9 test on how to get into it from USA Test Prep. All of the rules still apply to it, though. 3-hour time limit. Haley, I knew you were going to ask me that. I'm not 100% sure. Okay, because remember, a lot of these questions are very simple, like reflect this point, and you just count the blocks, and there's your answer. They're very straightforward questions. I tried to make them on OMHS, but it was taking me more time to make the problem than it took me to actually teach it. So it was just easier to give it to you in USA Test Prep this time. So that's where the test will be. Haley, I'll look that up for you. And if I don't get to answer it, you can email me that question. Cool. Yep. So the Unit 9 test will be in USA Test Prep. You'll see that open to you on Friday. I definitely recommend doing the review beforehand, because please remember, I can see how long you spend on the test, and I can also see when you open the test and if you close it and come back. So I can still see that on USA Test Prep. So if you're not following the testing rules, you're not going to be able to get a score for that test. So please make sure that when you sit down to take it, your computer is charged, you're prepared, and you've got 3 hours to do it. Okay? It shouldn't take you 3 hours. It really shouldn't. But that's how long you get. Oh, no. Are you there? Someone say if you can hear me. Hello? Can you guys hear me? Oh, phew. My power just flickered, so I thought maybe I lost you, and that would have been so sad. Okay. I don't know why my power just flickered, but if it does, keep an eye on your class announcements. Okay. Cool. John, I just thought you were very excited to say hello. That's okay. All right. So today we are going to cover symmetry, and we are going to cover dilation. All right, so starting with symmetry, we have 3 types of symmetry. We have line symmetry, point symmetry, and rotational symmetry. And I know this is not the first time that you have heard about this. You probably heard about it in a little more simpler terms, like folding a piece of paper, maybe. But we say that a figure has line symmetry if it can be mapped on itself by a line of reflection. In simpler words, can you draw a line where you would fold the shape and it would land exactly on top of itself? So for my triangle here, if I could draw a line, that would be helpful. Let's try actual line. If I drew a line here, I could fold that triangle on that line and it would land exactly on top of itself. So if you can draw that line of reflection, we can say that it has line symmetry. Point symmetry is if you can rotate your figure exactly 180 degrees. That's a fancy way of saying you can turn it upside down. If you can turn it upside down and it looks exactly the same, then it has point symmetry. So if I took this N, and now my copy paste feature works again, so let's try it. Okay, I'm going to snip my N. Copy. Whoa, that's a big N. Okay. Sure, we'll just make it ginormous. Okay, here's your N. Now, if I can turn it upside down and it looks exactly the same, then we say that it has point symmetry. Okay. technicals. Okay. And rotational symmetry says you can rotate it, but it doesn't have to be 180 degrees, just anything less than 360. So if this sun here, if I made the rotation the center of the sun, I could rotate this point of my sun to this point of the sun. The number of times you can turn it is, well, hold on. Let's count how many times I could turn it. So I could turn this point, I could turn it here, or 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 here, right? So I could turn this 1, 2, 3, 4, 5, 6, 7, 8 times. There's 8 different ways I could turn it, and it would land exactly on top of itself. So if you do 360 divided by the number of turns, so 360 divided by 8 is 45. That will tell you the degree of rotation. So if I turn this 45 degrees, this blue point of my sun will land on the green point. If I turn it 45 degrees 2 times, which would be a 90-degree rotation, then my blue point would land on my red point, and so forth, until it made it all the way around. So each turn is worth 45 degrees. So a rotational symmetry is just you can rotate it less than 360 degrees, and it would land on top of itself, where point symmetry says you have to rotate it 180 degrees. If a shape has point symmetry, then it has to have rotational symmetry, because this 180 degrees meets this less than 360 criteria. So if you're going to tell me it has rotational symmetry, or sorry, say that again. If you're going to tell me it has point symmetry, then it definitely has rotational symmetry. This point symmetry is just a very specific case of rotational, and we'll see an example of that. Okay, so here we go. We've got some examples. Looking at this first one, determine if the figures have line, point, and or rotational symmetry. And you can pick one, more than one, or it could be none. So looking at this, could you draw a line so that it folds on top of itself? If you think that you can, you should have whiteboard tools. On number one only, can you draw the line of reflection? What do you think? Yeah, somebody did it. Great. Anyone else? Anyone see a different one? Anyone see a different? Okay. Anyone see something different than those two? Seeing some good ones. Yeah, good. You got them all. Yay. Thank you, guys. Cool. All right. So hopefully you can see everyone's here. I'll do mine in yellow so that we can really see what's going on. We have a line of rotation here and here and here through all of the sides. But then we also have lines of rotation through the points. Now it got really messy. All right, no, it's not. Okay. Let's make it not so messy. No, it's all right. Sometimes messy is good. You guys did a great job. Okay, so we said here and here and here and here. I'm missing a couple. Here's one and here's one. Wow, it has a lot of lines. We really only needed one to say it had line symmetry. But it's possible that the question would ask, how many lines of symmetry does it have? How many lines of symmetry do you think this thing has? And you can type it in the chat. Okay, I see one person saying 4, one person saying 6. Someone says 8, 10. All right, let's count them. 1 line of symmetry, 2 lines of symmetry, 3 lines of symmetry, 4 lines of symmetry, 5 lines of symmetry, 6 lines of symmetry. This has 6 lines of symmetry. Okay. Here's the mistake that I see students make a lot of the times is they draw on all their lines and then they count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and they say 12. But be careful. They counted this one twice, right? Don't count them twice. Count the lines, not the points that you have out here. So how many lines? There are 6 lines. Now, this is really cool. On your regular polygon, this rule will work for all. How many sides did this polygon have? It had 6. How many lines of symmetry does it have? 6. Do you think that's a coincidence? No, it's not. So if you have a regular polygon, whoa, that's a fat pen. Let me try that again. If you have a regular polygon, meaning all the sides are the same and all the angles are the same, then your number of sides, or n, will equal the number of lines of symmetry. Now that's only true for regular polygons. So this hexagon was great. Okay, now let's talk about point. Does it have point symmetry? Can I take my hexagon, turn it upside down, and it look exactly the same? Yes, I can. So it has point symmetry. And as soon as it has point symmetry, well, it immediately has rotational symmetry. If you find yourself checking point, then you should definitely check rotational. So what is the degree of rotation for this dude? So how many degrees would I need to turn it to get this point onto this one? Well, how many times could I turn my hexagon? 1, 2, 3, 4, 5, 6. 6 times. So 360 divided by 6. Well, that's 60. So the degree of rotation is actually 60 degrees. Okay, so just some questions they might ask you in addition to deciding what kind of symmetry it has. They might ask you how many lines of symmetry it has. They might ask you what the degree of rotation is. So to find your degree of rotation, how many times can you turn it? 360 divided by that number. Now, could I turn this 120 degrees? Certainly. 120 degrees would be 1 260s. I could turn it 180 degrees. That would be 3 turns. I could turn it, let's see, it was 180 plus 60, 240 degrees, and it would land here. So each of these turns is worth 60 degrees. Okay. Clearly, we're not going to choose none here because we chose 3. That would be kind of silly, wouldn't it? Okay, let's look at number 2. All right, you're going to see a poll come up on the screen there. Number 2, does my triangle have line symmetry? Yay or nay? Yes or no? Does it have line symmetry? Could I fold my triangle in half? If you don't see the poll, I'm guessing you're on a different device. You can enter your answer in the chat. But if you see the poll, just go ahead and give me your answer. Oh, thank you, Brianna. All right, thank you. Anyone else want to throw their answer up there for me? Okay. If you said yes, you are correct. Okay. Most of us said yes, which is good. The line that you could draw would be right here. Well, kind of. If I could draw a straight line with my board, try again. There we go. Or maybe you said right here. Or maybe you drew a line here. All of those would be lines of symmetry. I could fold this triangle on any of those lines and it would land exactly on top of itself. So it has line symmetry, yay. And someone in the chat, I think even said it has 3 lines of symmetry, and you're right, it does. Now, point symmetry. Does it have point symmetry? Can I turn this triangle upside down and it looks exactly the same. Good, Valeria. Yay, Haley, you're right. Okay. And if you're not sure, maybe take your notes and turn them upside down. I'm going to do my best to turn it upside down on your screen here. There it is. Okay. Get my eraser. There we go. If I were to turn it upside down, whoops, come on. Okay, it's still a triangle, sure, but this time the vertex point is at the bottom, right? This doesn't look like exactly the same way, so there's no point symmetry here. You're right, Lydia. Yes, Axel, perfect. I like how you said that. Axel says the point wouldn't be in the same spot. You're right. Okay, so now, could it have rotational symmetry? So just because it doesn't have point doesn't mean it's not rotational, right? Can I still rotate it? Well, this is a regular triangle, equilateral. Oh, here we go. I could turn it so that this point landed right here. Okay, so how many degrees of rotation would there be? Yes, Lydia, perfect. Anyone else? What would be the degree of rotation? 3 turns, Hannah. Very good. So we're going to do 360 divided by the number of times I could turn it, or the number of sides of the polygon, and we get 120. So each rotation would be 120 degrees. So it has rotational. It doesn't have point, but it does have line and rotational. Yay. All right. How about number 3? Let me think of number 3. I think it has line, point, rotational, or none. So whenever I ask myself about line, I start just kind of drawing some lines in there. Could I fold it here? No, that wouldn't work. Could I fold it here? Oops. Not gonna let me go back, huh? Nope, that's not going to work either. Okay. What about the diagonals? Nope, that's not going to work either. Huh. No line of reflection, none. So this one doesn't have a line of reflection. How about point? If I turn it upside down, would it look the same? Nope, it wouldn't look the same. If I turned it upside down, this point would end up being like down here. That's not the same. Okay, so not point, not line. Rotational, could I rotate it? Well, this is not a regular polygon, so this whole like number of sides, number of lines of symmetry, and the whole 360 divided by the number of turns, that wouldn't work. Nope. You can even try turning your paper or snipping it and rotating it. You'll notice that it doesn't land on top of itself until you get all the way back to the beginning. So the only way that I can turn this shape and it land exactly on top of itself is if I turn it exactly 360. But rotational said you had to turn it less than 360. So here's a great example of a figure that has no symmetry. Okay, hopefully this is making sense to us. Take a moment, look at number 4. Go through your choices. Line, could you draw any lines? Point, could you turn it upside down? Rotational, could you turn it less than 360 and it land on itself? Or is this none? What do you think? I'm going to put a poll up there. We're going to call them A, B, C, D. So in the order that you see them. Line, point, rotational, none. A, B, C, D. What do you think? Okay, and I'm going to need an answer on this one. So if you're not answering, I'm going to assume you're not there. If you don't see the poll, go ahead and answer in the chat. Otherwise, just answer the poll question. All right, last call for answers. Anyone else? Okay, if you find yourself removed from the room, I'm assuming you're not here because you're not answering. Okay, cool. If you said none, you are correct. You're right. This one doesn't have any. If you said something other than none, let's talk about why. So for your line symmetry, there's really nowhere that I could draw a line on this and it fold exactly on top of itself. It would be really close, right? But it's not like this wouldn't fold. And no matter where I put this, definitely not going to fold exactly on top of itself. And any vertical line here wouldn't work, right? Because if I put a vertical line here, come on, line, that's definitely not going to fold on top of itself. So this one did not have line symmetry. As for point symmetry says, can you turn it upside down and it look exactly like itself? Well, it would land on top of itself, really. So if I took this and turned it upside down, why it pastes in there so ginormous. Sorry. And turn it upside down. Well, now it's like facing the wrong way, right? It does not landing exactly on top of itself. It's just rotated, but it's not being mapped exactly onto itself. And then for rotational, I could rotate this, right? And it's not going to land exactly on top of itself until I get back to 360. If it was a 45, 45, 90 triangle, would it have a line of symmetry? Yes, it would. Yep. I would say that all isosceles triangles have a line of symmetry. Let's try one. Let's see if I can draw one. Probably not. Okay, so if this was a 45, 45, 90, your line of symmetry would go right down the middle, right? As long as this was the 90-degree angle up here. Okay, if that was the 90-degree angle, then and this was your 45s, then it would land exactly on top of itself. Very good question. Okay. All right, let's look at some other examples here. There's all kinds of fun examples in these notes, and I'm not going to go through every single one of them. Let's see. What do we want to do? Let's look at this page. All right, I'm going to turn your whiteboard tools on. I want you to pick one on the screen, just one, and maybe one that you definitely know the answer to, and just give me a check mark. So if you think that number 9 has line symmetry, go ahead and give me a check mark on the line symmetry. If you think it has point symmetry, maybe you'd give me a check mark on point. Just put one check mark on the screen on one that you think might be correct, and then we'll talk about it. So here are your whiteboard tools. There you go. Pick one and give me one answer for it. What do you think? I'll give you a minute or two there. All right, please make sure you're answering the question, Faith. All right, we got some good stuff going on. We might agree or disagree with some of these answers, but for now, we're just putting what we think on the board. Seeing a lot of really good stuff. All right, we have all the right answers and 2 wrong ones. Anyone else want to put your answer up there before we talk about them? All right, now I'm going to change the direction slightly. If there's an answer on the board that you don't agree with, can you grab your pointer tool and just go point to it? Yeah, a lot of people in number 9, I agree. There's one more. Number 9 people, I agree. There's one more incorrect answer up there. Can you find it? Number 10 is right. Yeah. Look at all those little arrows go. I love it. You're right. All right, let's talk about the 2 that aren't correct. You can check yours with the ones that are here. Oh, Max, I see what you're doing. I see that. Cool. Let's see how many arrows get stuck on my screen because that happens sometimes. All right, so if you pointed up here to number 9 because you disagreed with an answer number 9, I completely agree with you. The one that we should not have here, and it's okay if you put it there, I think whoever answered it anyway, because now we can learn from it. This one right here. This one kind of looks like it has line symmetry, right? But when you start to draw the lines in, you start to realize there's really nowhere to draw the line in to fold it. Because if I fold it along this line, well, then this triangle here ends up over here on the left. And if I start drawing in like some diagonals, well, it's not landing exactly on top of itself. So this one does not have line symmetry. But thank you, those of you who were participating anyway. I really appreciate it. Lets me know you're there. All right, and then if you pointed down here, someone even tried to exit out for us. This one down here, number 13. Number 13 does not have point symmetry, and the reason for that is if I were to turn this dude upside down, see, you would end up having this part down here. But there's no, like, I don't know, what do you want to call that, a leaf? There's no actual leaf there for this. So this top part would end up down here, but there's nothing there for it to land on. So that would not have point symmetry. But it does have rotational symmetry, so that's good. Nice. Everything else was right. You guys rock. All right, let's move on. There's so many practice problems. Oh my goodness. Definitely you can practice them and then check your answers on OMHS. If there's any that you disagree with or you don't understand why I have my answer and you have a different one, definitely go ahead and reach out to me and I will try to explain it to you, probably with a video. All right, now we are going to move on to dilations. Dilations are not an isometry. We're going to take our shape and we're going to change it, but it's not an isometry. Okay, so think about the last time we were live, last Wednesday, we discussed an isometry. Anyone remember what an isometry is? You want to type it in the chat? An isometry is, yep, Hannah, you're right, pre-image. It relates your pre-image and your image. How? Equal. Yay, Faith, gold star for you today. All right. So an isometry is when your pre-image is equal to your image or congruent. They're the same shape. So today we're going to talk about a dilation. Dilations are not isometries. So that means that our pre-image and our image, they are not going to be congruent. See, you can even see the picture there, right? I've got triangle ABC and then triangle A prime, B prime, C prime, and it's smaller. It's not the same size. So even though they're not congruent, they are what we call, anyone know the word for when they're not congruent, but all of their sides maybe are proportional? Similar. Nashmia, awesome. Haley, awesome. Yep, they're similar. Okay, so they're not going to be congruent. They're going to be similar. Let's fill in these blanks. So in a dilation, we are going to enlarge or reduce a shape. So the enlargement, the big word, or reduction of a figure. Okay. And some of you started using this word in the chat, and you were totally right. You said they're scaled. Yeah, and that number is called the scale factor. So the scale factor will indicate how much the figure is going to get bigger or smaller. For the purposes of our notes, just so I have something to like refer to that scale factor, I'm going to call it K. You can call it whatever variable you want. Yep, there you are, you're right. So when your scale factor, so when K is greater than 1, it's bigger than 1, then your dilation is going to be an enlargement. It's going to get bigger. And when K is less than 1, then the dilation will be a reduction. Okay. Now your scale factor isn't going to be negative. I mean, technically it could be, but we're not going to work in that world. So really, when I'm saying it's less than 1, I'm saying like greater than 0. Oh, that's supposed to be, let's try that again. Greater than 0, but less than 1. So what are some numbers that are greater than 0, but less than 1? Any fraction that's less than 1. Navira says 1/4. That's perfect. Lydia says a half. Perfect. Ooh, Haley got fancy. 0.7. Yep. Now, usually our scale factors are going to be written as a fraction. Okay. So usually you're going to see a fraction. All right, you're going to find this really easy, I think. Let's look at an example. So we're going to graph the pre-image with the points. In this case, it's RST. And then the scale factor is 2. And different questions will ask this different ways. So like on the SOL, it might just say the scale factor equals 2. Just be aware that sometimes the scale factor could be given like this, or it might actually be in words. The scale factor equals 2, something like that. So I'm going to go ahead and make this bigger so I can see it. My old eyes gets dizzy on these. Here we go. All right, -5, 1. 1, 2, 3, 4, 5, 1. I'm going to label that R. S is at -3, 4. And T is at 2, -1. There it is. What a pretty triangle. Me too, Faith. Do you remember our rules for translations where we had like X, Y's mapped onto? You could think of this as taking our X, Y and mapping it, but this time we're going to multiply the X value by the scale factor and the Y value by the scale factor. Okay, so this scale factor is what I'm multiplying each coordinate by. So for R, I'm going to multiply -5 times 2 and 1 times 2. There we go. Now we have a new point. -10, 2. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So R goes here, or R prime now, right? Because we get to give it the new name. S is at -3, 4. So we're going to multiply each coordinate by 2. So S prime becomes -6, 8, just multiplying by the scale factor. So -6, 1, 2, 3, 4, 5, 6, +8. And we label that S prime. And then T was at 2, -1. So multiply each of those by 2 for -2. 1, 2, 3, 4, 1, 2. So this is the same triangle. It's just enlarged. And you guys have seen me do dilations almost this entire class when I was copying and pasting images. So, I don't want to lose it. Well, we'll see what happens. I might lose my writing. It's a risk I'm willing to take. So you saw me put like a picture up there, right? And I didn't like it. So I started dragging it bigger. Oh, but that was too big. So then I made it smaller, but then maybe that was a little too small. So I got it bigger. Every time I made it bigger or smaller, I was performing a dilation. I just wasn't calculating the scale factor. But every time I made it bigger or smaller, keeping it the same shape, I was performing a dilation. I do this all the time in a Word document when I'm trying to insert images and I need to make it fit. So I'm sure that you've been doing this a lot too, as you're using your snipping tool and trying to get it fit in there too. So as you're looking at your, oh, I didn't save it, shape, your triangle, which mine has now been deleted, it should look like the same triangle, just bigger. And it makes sense that it got bigger because our scale factor was bigger than 1. Okay. A lot of times you might see a problem like this, and the question is only going to say, will your image be a reduction or an enlargement? And all you have to do is look at that scale factor. If the scale factor is bigger than 1, it's an enlargement. If the scale factor is less than 1, then you're going to have a reduction. So I'm going to skip number 2 since that's just another enlargement. Let's go see what a reduction would look like. So here, number 3, my scale factor is 1/2. So after I'm all finished graphing this thing, my, rhombus should be smaller. Okay, if you graph it and your rhombus is bigger, you made a mistake. So you're going to graph those 4 points. -10, 2, label it J, -2, 8, K, 6, 2, and -2, 4. Uh-oh, did I make a mistake? Oh, -2 and -4. Oh, -2, 8. That was silly. Yes. We got so excited to do the dilation that I stopped graphing correctly. -2, 8. There it is. Nope, that was 9. Good grief. -2, 8 is K. L, 1, 2, 3, 4, 5, 6, 2, and -2, -4. There we go. Make sure J is right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 2, -2, -4. Wow. We've all had those days. -2, -4. Hannah's just like, yeah, she'll figure it out. She'll figure it out. All right, you can connect those with lines if you want, make it a nice pretty rhombus. There it is. Okay, and I love that these problems tell you what the shape is. So that way, if you do plot the points wrong, like I started to, you can at least tell that it's wrong because mine clearly wasn't making a rhombus. Okay, now we have to multiply each coordinate by the scale factor. So multiplying -10 times 1/2. Remember, multiplying is the same as, or dividing is the same as multiplying by the reciprocal. So if I want to multiply by 1/2, in my calculator, do I have to type times 1/2? I'm sure that's not what you're all typing. What could you actually type in your calculator instead of multiply by 1/2? You could multiply by 0.5. Lydia, I like what Lydia did. Lydia said, well, I just did 10 divided by 2. It's the same thing. Multiplying by the half or dividing by 2 is the same thing. You know, whatever makes it easier to type in your calculator. If you just like multiplying by the half, then multiply by 1/2. Or you could even think of it this way. What was it? Algebra 1? Was it like Algebra 1, Unit 1, you learned the words of math where you learned like is means equals and sum means plus, right? Remember kind of learning those like translation rules, like sum meant plus and product meant multiply and all that stuff. Well, if I said 1/2 of 10, of means multiply, 1/2 of 10. But what is, if you think of it not as like multiply, what is 1/2 of 10? Well, 1/2 of 10 is 5. Okay, so there's a whole spiel on multiplying by 1/2. As long as you can get 1/2 of -10 and 1/2 of 2, you're good. And then we can graph that point. -5, 1. 1, 2, 3, 4, 5, 1. There it is, J prime. -1, 4. 1/2 of -2, 1/2 of 8. So -1, 1, 2, 3, 4. K prime. L is prime would be at 3, 1, half of 6, half of 2. And M prime, half of -2 is -1, and half of -4 is -2. There it is. Okay. Does it make sense that my blue rhombus is smaller? Does that make sense? Yeah, it does, right? Because our scale factor was less than 1, which meant that we're taking that red rhombus and we are going to reduce it, make it smaller. I saw someone ask a question about graph paper, but I have since lost it in my chat. This is probably one of the transformations that you don't really need the graph paper to be able to find these coordinates. I know someone asked me that. I just don't know where it went. Okay, so that was finding the coordinates of a dilation. Fun. Okay, and there's all kinds of practice problems for you there. Lots of practice problems. Just real quick, look at number 5. I want you to give me a green check if you think this is going to be an enlargement, or give me the orange X if you think it's going to be a reduction. Ready? Go. In number 5, do you think that's going to be an enlargement or a reduction? Seeing a lot of good answers. Yeah. Good job, John. All right, so this was kind of a tricky question, but it's definitely worth bringing to your attention. If you said it was an enlargement, I completely agree with you. Yes, this was an enlargement. Okay, why is it an enlargement, Miss Grandy? It's a fraction. Okay, it's not because it's a fraction. Being a fraction doesn't mean it's an enlargement. Okay, this has to be, you have to ask yourself, is it greater than 1 or less than 1? And 5 over 2 is really like 2.5. That's greater than 1. So your scale factor was greater than 1. So we had an enlargement. That is the one kind of tricky question that students tend to make. As soon as they see a fraction, they think it's going to be a reduction. No, no, no. The scale factor has to be greater than 1 to be an enlargement and less than 1 to be a reduction. Doesn't matter if it's in a fraction form or however. If that scale factor is greater than 1, you got an enlargement, even if it's an improper fraction. Cool. All right, now we got one more skill here with our dilation. Could we come up with the scale factor? Okay, so just like when we were talking about our transformations and translations, we always start at our pre-image and we end up at the image. So D will go to D prime, or E will go to E prime, or F would go to F prime. You can choose. Choose one of those 3 points. I'm going to choose D. Find the coordinate of each one. Find the coordinate of your pre-image. So in this picture, D is at 0, 6. And then find the coordinate of the image. Where did D go to? Well, D went to D prime. D prime is at the point 0, 2. Think of the word scale factor for a moment. Okay, we've heard this word factor before. What's a factor? If I talk about factors, what do you start talking about? Numbers. What are you doing with numbers? If I said, what are the factors? Like, what are the factors of 6? Right? Multiplication. Thank you. Yeah. And that's exactly what a scale factor is. What are you multiplying the number by? So the 0 doesn't help me out a whole lot, right? Because 0 times anything is still 0. So we're going to look at the y coordinate. What do I multiply 6 by to get 2? Good job, John. If you're saying 3, you're thinking on the right track, but it's not quite 3, right? Because 6 times 3 is 18. So I'm seeing a lot of good answers over there. here's a foolproof way that will work every time for you. Okay, you ready for it? Here we go. 6 times my scale factor has to equal 2, because whatever I multiplied 6 by, I got 2. Now you've got this nice simple equation to solve. How do we undo this multiply? Oh, we divide by 6. Okay, well, 2/6 is 1/3. So if you were typing 1/3 in the chat, you're right. It was 1/3. If you were saying divide by 3, yes, you're right. 6 divided by 3 is 2. But the question is, what am I multiplying by? And so when you say divide by 3, dividing by 3 is the same as multiplying by 1/3. But if you can think about it the way I just said it, the number times what, the scale factor, has to equal the image. So the pre-image times the scale factor will equal the image. Set up your equation. Your pre-image times your scale factor equals your image, and then just solve for your scale factor. Usually it's just a simple divide. Well, when you do the 2 divided by 6, yeah, because you'll divide both sides by 6, 2 divided by 6 reduces to 1/3. If you wanted to go the other way, I just caution you with that. Like you could say, okay, well, 6 to 2, I'm multiplying, so 2 to 6, I'm dividing. Maybe that's what you're thinking. That would work. Let's look at number 12. John, since you're the last one I see there, what letter do you want to use? Do you want to use W, X, Y, or Z? X. All right, so in number 12, let's find the coordinate of X. Yeah, Lydia. Yep, absolutely. Lydia, that's perfect. All right, so X says, okay, well, or not equals. It's at the coordinate 2, 0, and then it ends up at X prime, and X prime is at the coordinate 8, 0. So this one's a little easier. So what do I need to multiply by? Oh, and this is a nice one, right? Well, 2 times something, my scale factor, will have to equal 8. So this is a nice easy one because it's just an enlargement. 4. Very good. Okay, so I forgot to give you your attendance word. Luckily, it's been all over these pages this whole time. Here you go. Your attendance word for today is scale. There it is. Scale. Oh, Faith, you tried to guess it. Write that down, circle it, highlight it. Okay. So today we talked about symmetry, line symmetry, point symmetry, rotational symmetry, or none. And we talked about dilation. We can make our figure larger or smaller, which means it's not an isometry because our pre-image and our image are not congruent. They are similar instead. So we figured out how to find the new points using our scale factor. And we saw 2 examples where we had to actually find the scale factor. Very cool. And that brings us to the end of the lesson. Oh, this is day 2. Okay, there's an exit ticket for you. Maybe do a few practice problems if you need to. And don't forget to do the attendance word quiz, the attendance quiz. Okay, short unit, short test. It'll be on USA Test Prep. You'll see it on your plan on Friday. Once I say that attendance word, I can't go back to it. Oh, yeah. Haley, give me 1 second. I'll look it up.